All right, so now we are into, again, we've been looking at finding the slope at 1 point, as I would say, instantaneous, although it's supposed to be 2, but it's not really because, again, those 2 points are so close together. We're finding the slope at 1 point. The next thing we're going to look at is what's called proving maximum and minimum values, in which case we're dealing with slope again. Now, I'm going to pretend that my little pen here is the slope of the line. Now, if I follow this graph, I'm going to find or look at 2 specific spots on my x-axis, W and X. Now, as my pen, again, is the slope, and I would say that my fingers here are the point where I'm calculating the instantaneous slope, it would be positive. As you can see, my marker is pointing up, so it would be positive slope. It's still positive as my fingers go along. Now, it's starting to turn a bit here. Now, as I turn and I get to the very top of the hill, right? You see my fingers are at the very top. They're at an X value of what I'm calling W. That marker is dead flat, which means the slope at the very top of the hill, the tangent line, the slope of it is 0 because it's a horizontal line. Now, as I keep moving this pen down the line, you can see now that my pen is turning downwards. Now I have a negative slope. I have a negative slope. I have a negative slope. You can see it now. I really have a negative slope. But now my pen, again, if my fingers are where I'm looking at the instantaneous slope, you can see my pen turning again. And at the very, very bottom of a graph, again, I have a tangent line there that has a slope of 0, horizontal line. And then, of course, as I keep moving, you can see now my pen's turning up. I have a positive and positive slope. The big thing here is that the slope of a tangent line is 0, which means it's flat. It's a horizontal line at a high point, which is a max, or a low point, which is our minimum value. So when you find the instantaneous rate of change and it is 0, that means that we have a max or min at that spot. And then to prove it, what we can do is, for a max, which in this case would be when our x value is W, I guess, as I wrote. So in this case, that top spot would be f of W. And for f of W, that value is going to be the highest amount of anywhere around it. So that means f of W is going to be greater than, I don't know, we go backwards by amount of h. So I put f of W minus h. And we go a little bit ahead, h amount. So it'd be f of, or W plus h. So anywhere near this f of W, to the left of it, to the right of it, is going to be a smaller amount because it is a max value. Now, the same idea can be used for what I use as an x value of x, and that's a low point. So for a min, f of x is going to be less than. And again, I could pick some h value before and after. You subtract an h or you add an h. So it's going to be less than those values. So f of, say, x plus h and f of x minus h. Now that's the theory behind it, okay? How the heck are we going to use this for doing questions? That's what I'm going to get to. All right, the key here is that right here, the slope of a tangent line is 0 at a max or min value, because that's where, when you find the instantaneous rate of change, your slope is a nice horizontal line, which means it has a slope of 0. So I get to example number 1 here. All right, so example 1 says the height of a glider thrown from the top of a hill is modeled by the function h of t. Might as well write it down here. I know I'm going to use it. H of t is equal to negative 5t squared plus 20t plus 55. All right, so that's the equation where h is height and t is time in seconds. It says prove it, that the height of the glider reaches a maximum at t equals 2. So we're going to prove max at t equals 2. All right, so what we're going to do is we're going to find the instantaneous rate of change at 2. It has to be 0 to prove that it's a max or min, and then we're going to prove, well, it's going to be a max or min, and then we're going to prove that it's actually a max. So we're going to find the limit as h approaches 0. All right, now our t value there is 2, so in our function here is the h function. So our first one here, we're going to have h is 2 plus h minus h of 2 all over h. There we go. So we're going to find our instantaneous rate of change at 2. Now, again, it's easier for me to just find h of 2 by plugging into the formula. All right, so let's see here. I'm going to tell you that I already plugged it in. All right, so that's just math. When I put a 2 into the equation, I get 75. All right, I just don't have the room to do all the calculations, but again, it's just substituting into our function. But now what I got to do is I got to do this part where I substitute 2 plus h into the formula, just like I was doing earlier. All right, so we got the limit as h approaches 0. All right, so now, again, I'm going to do square brackets just to keep things clean as possible. So I got a minus 5, t squared. So instead of t, I'm putting in a 2 plus h, and it's squared, plus 20 times that 2 plus h, plus 55. And, of course, I can't forget my minus h of 2, which is minus 75. And that is all over h. All right, now that equals the limit as h approaches 0. So again, I got my square brackets here. I'm going to go a little, no, I won't go faster. Slow it down. All right, so I'm going to do my binomial squared again because I know people have issues with that. All right, so again, I'm going to go 2 squared. That's 4. Then I go 2 times h times 2. That's a 4h. Then I square the last term, so that's an h squared. All right, then I can simplify this part a little bit. 20 times 2 is 40. 20 times h is 20h. Plus I got the 55, and I got the minus 75. I don't even need this square bracket anymore. There we go. Just want to keep it. And, of course, it's all over h. All right. See if I can do this in the proper amount of room here. All right, so as h approaches 0. So now, again, I still have to do my rainbow rule here. All right, so minus 5 times 4 is minus 20. Minus 5 times 4h is minus 20h. Then I got a minus 5 times h squared, minus 5h squared. All right, you know what? I got some of this stuff I can put together, these numbers. I got a 40 and a 55. That's 95. Minus a 75. That's plus 20. So I'm just simplifying things again. I can't forget I got my 20h here also. All over h. All right, so here's where we're at. Now, let's see here. Again, this is always a good little checkpoint because, again, if you mess up expanding out your polynomials, things can get ugly, can get messy. There's no doubt about that. But look at this. I got a minus 20 and a plus 20. I'll put those together, and they're gone. That's a net 0. But then I also got a minus 20h and a positive 20h. Well, there's a net 0 also. There we go. All right, so now equals the limit as h approaches 0. All I've got left there is that minus 5h squared. And on the bottom here, of course, I've got my h, because that's our problem. We can't substitute. We can't divide by 0. Now look at, I have h here and an h squared up here. So I'm going to factor out an h, or I just divide both sides by h. So that gets rid of the little 2, and this h is gone. And so now all I've got is a minus 5h there. I do not have an h in the denominator. So now, I guess I'll rewrite it. I got a little bit of room here. The limit, as h approaches 0, I got a minus 5h. I can substitute now in my h value of 0. And guess what I get? Minus 5 times 0 equals 0. So this is what that's telling me now. Because I now know the instantaneous rate of change at t equals 2 is 0, there is a max or min at t equals 0. Or sorry, t equals 2. We did it at 2. So now I know there is a max or min. I don't know which one yet, but I do know there is a max or min. So now I'm going to get back to this part. How do I show that it is a max or a min? Well, I'm just going to do a quick substitution here. Oh, make sure it's nice and dry. All right, so here's how, first off, when I put into the equation h of 2, I found it to be 75. So now to figure out whether it's a max or a min, I'm going to find out a value just before 2, t equals 2, and just after t equals 2. So what I did was I found out h of 1.75. I plugged that into this formula right here, and the value I got was 74.6875. Okay, so it's looked like it's going to be a max, but I also have to check a value after t equals 2. So I also checked out h equals 2.25. And guess what? I got the same thing, 74.6875. And so because a little value, a little bit before t equals 2 is lower amount, and a little bit after t equals 2 is a lower amount, well, therefore, there is a max of 75 at t equals 2. There we go. So the first thing we did was, just want to recap because we're going to do another one, is we found the instantaneous rate of change. We found that slope to be 0. That means we had to have a max or min. And then just by finding values a little bit before our t value and a little bit after our t value, we were able to determine that it actually was just a max. Well, it is a max. It's got to be one or the other, a min or a max. We figured out it was a max. Any questions there before I give the board a flip? All right. Let's see here. Oh, this thing's not the easiest thing to turn over, if you might have noticed. All right, so example 2. Try it again here. All right, so we have an alligator, yikes, floating on the surface of water, dives towards the bottom of a stream to snatch up food. Okay, if the depth of the alligator is represented by the equation, h of t equals 2t squared minus 12t plus 13. All right, so prove the height of the alligator reaches a minimum at t equals 3. Okay, so this is all in seconds here. All right, so we want to prove there is a min at t equals 3. All right, so the first thing we're going to have to do is find that instantaneous velocity at t equals 3. Prove the slope is 0 there. All right, so we have, again, we're going to look at the limit as h approaches 0. And again, it's going to be h of 3 plus h. Oh, nice with the height function. These h's are different. Minus h of 3 divided by h. All right, so again, these little h's are different than this h. This h is for this function, height. Probably bad use of variables, but h is always used for height. What am I going to do? All right, now, again, before it gets messy, I'm going to find h of 3 over here just by plugging in 3 into the equation. All right, so I'm going to have 2 times 3 squared minus 12 times 3 plus 13. Let's see here. 3 squared is 9 times 2 is 18. 12 times negative 12 times 3 is minus 36 plus 13. Let's see here. 18 minus 36 will give me minus 18 plus 13. I'm going to minus 5. Okay. So after 3 seconds, this alligator has a depth of minus 5 meters relative to where it started, I guess. All right. So now I'm going to, again, substitute in here. So I'm going to find the limit as h approaches 0. I got to find, again, I'm going to use square brackets at the start just to separate things. So 2t squared is going to be 2 times 3 plus h squared. Minus 12 times t, which is going to be minus 12 times 3 plus h. Plus the 13. Square brackets just to show the substitution here. And then I got my minus h of 3, which is, watch this. Minus, there's a minus sign in the equation. There's a minus sign in this number. That could be a mistake for people for sure. And divided by h. All right. So back to what I've been doing before. All right, so I'm going to do my binomial square here. So I've got the limit as h approaches 0. Let's see here. I don't need square brackets anymore. Maybe I don't. I don't. All right. So let's see here. I square the first term. 3 squared is 9. Then I go 2 times h times 3. Well, 2 times h is 2h times 3 is 6h. All right, and then square the h, the last term. There we go. There's that part. Then minus 12 times 3 is minus 36. Minus 12 times h is minus 12h. Plus 13. And then this thing over here, I get a minus minus. So 2 minus signs come together, give me a plus 5. All over h. All right. So now I got to do the rainbow rule here. All right, so here we go. Limit as h approaches 0. Let's see here. 2 times 9 is 18. 2 times 6h is 12h. And 2 times h squared is 2h squared. All right, what else we got here? I got to put these numbers together. I got minus 36 plus 13 plus 5. Well, minus 36 plus 13 is minus 23. Plus 5 is a minus 18. And I got this minus 12h. So I'm just collecting like terms when I can make it happen. And again, it's divided by h. Now, here's something we got. I got an 18, just looking number-wise, 18 minus an 18. Well, that's a net 0. Gone. Then I got a 12h minus a 12h. That's also a net 0. They're gone. All right, so now let's see here. I got the limit as h approaches 0. On the top, after all that, I got 2h squared divided by h. Now I get a little more room, so we'll simplify it a little bit here, where now I have equals the limit as h approaches 0. Let's see, I factor out an h, so I did a little bit different this time out here. Same idea. All over h. And just as we did before, those h's divide each other out. And now I don't have that denominator of h in there. And so I can plug a 0 into 2h. Well, 2 times 0 is 0. And that just means the instantaneous rate of change at that point is 0. So therefore, there is a max or a min at t equals 3. All right, now, figuring out. Well, it says it's a min, but I might give you a question that says, hey, is it a min or a max? So this time I'm telling you it's a min. And so I already figured h of 3 out is equal to -5. Then what I could do is figure out a number before 3. So like I did h of 2.9. All right, so I substituted 2.9 because it's just before h. Usually you want to do a tenth. You don't want to go up. I think the last example I did 0.25 difference. Usually you want to stay within 0.1 or 0.01. All right, so very small amount. So I did h of 2.9. I plugged that. I used my graphic calculator. And I plugged it into the equation. And I got negative 4.98. And then I did the same amount after 3. So I looked at h of 3.1. So I plugged h of 3.1 into my equation. And guess what? I got the same thing here. I got negative 4.98. So which one's the more negative number? H of 3. So we just proved that any value around h of 3 is higher. It's bigger. It's less negative, not as deep. And so therefore, there is a min value of -5 meters, so that's the depth, at t equals 3. And there again, that's how we prove our maximum min values, is we look at the instantaneous rate of change. We find that that slope is 0, again, by using our formula for finding the slope of a tangent line, which again means you find the slope essentially at 1 point. It is 2 points, but the points are so close together, they're really 1. And then we have to find values just a little bit short of that x value and a little bit longer of that x value, and prove that it's either higher or in this case, or higher in this case, in my first example, lower.